Hello. So, thus far, we've discussed definite integrals and indefinite integrals as sort of completely separate things, right? So, definite integrals, these are the sort of perfect approximations of the area of some region bounded by some function, right, along the top, and the x-axis, and some interval a to b, right? So it's that weird finding a perfect area of a shape that has a curved edge. Indefinite integrals, on the other hand, was like this whole other thing. It was a class of all possible antiderivatives. It was reversing the derivative process. So we had sort of the infinite Riemann sum for the definite integrals, and then we had sort of reversing the derivative idea for the indefinite integrals. Now, it turns out these two seemingly completely unrelated things, these completely unrelated ideas, are actually the same thing, which sort of justify why we've been using the same notation almost. But to sort of establish that, that is what the fundamental theorem of calculus is. And the fundamental theorem of calculus, or FTC, comes in two parts. So in this video, we're going to start with the first fundamental theorem of calculus. So as a sort of starting sort of spot to understand what the first fundamental theorem of calculus says, remember the indefinite integral is the process of trying to reverse a derivative. And the sort of idea is that if indefinite and definite integrals sort of really are the same thing, which is what we're claiming here, then there should be a way to relate the definite integral to the derivative process and vice versa, right? Like we should be able to relate definite and indefinite integrals to one another. That's the hope. Now, to this point, we've discussed definite integrals using these concrete values for bounds, actual numbers, right? Like we label them A and B because we don't know what they are, but if we had like a specific problem, we're talking about, find the area of the region between x equals 3 and x equals 17, right? We have actual values for these things. But it turns out there's really no reason we couldn't put non-constants as bounds. So in particular, suppose we have some function f of t that makes sense to try to reverse the process here. And we consider the definite integral, right? 0 to x of this f of t dt. So instead of looking at this as like 0 to 5, I'm putting an x on the top. So what does that mean? Well, the lower bound, still a constant, just like normal. So this is still a thing that we sort of use, just like we've always done. But the upper bound is now a variable. So the question is sort of, what is that variable doing? What does that mean? Now, what that's telling us is that the right-hand bound is set by some input, right? As x changes, that right-hand bound will move, and thus the area will inherently change as we change that value of x. So as a way of sort of looking at this, as x changes, the area of the shaded region also changes. So in particular, if x changes from 3 to 6, or from 6 to 9, or back again, right, 9 to 6, that total shaded area is changing, and so as x changes, that area changes. Now we can think of that as sort of the total area of this definite integral is some kind of function of x, right? If you put in a value for x, then you can calculate that area. But that tells us that the resulting area is dependent on x, and thus we can think of the value of that definite integral as being a function of x. We can represent this thing as some, capital F of x, where that x is now the input that tells us where the right-hand bound is in particular. Okay? So now we can state the first fundamental theorem of calculus, FTC I. So sort of, again, as usual for these theorems, I'm going to state it in the full math speak and then sort of translate it. So if f is some, right, from r to r is some integrable function, and we fix some a and r, some constant, and we suppose there's some function f of x. There's some way of representing this integral so that we have the integral from a to x, that definite integral of f of t, is f of x. Then the claim is that f prime of x is f of x. So what does that mean? Well, that's telling us, okay, if we take the definite integral of some function, from any real number to x. So we think about that as, just as we did before, we use 0, but turns out we can use any letter we want, any value we want as the lower bound. But the upper bound is some x, and we want to represent that full area as some function, f of x, right? So as x changes, the total area will change, and to know what that area is, we call that thing capital F of x, right? Whatever that means. Well, this is claiming then that f of x, that capital F of x, is actually an antiderivative of little f of x. In other words, the function that represents the area as a function of x is the antiderivative of the integrand, which means that we now have a link between definite integrals and indefinite integrals, right? Because the integrand, the part inside, if I reverse that, if I get an antiderivative, that's what the indefinite integral is supposed to represent. So this is telling us, hey, I actually can find that area, that value, at least when the upper bound is sort of this variable x, I can find that thing by using the antiderivative. So indefinite integrals were always the antiderivatives, but now we have antiderivatives showing up in this definite integral situation. And this gives us a nice way to represent the area of that region, at least, again, when it's in the form of some function of x, okay? All right, so what do? So we formed the first of our relationships between these indefinite and definite integrals, right? Remember, the FTC fundamental theorem of calculus comes in two parts. So we've got one of those two. In particular, if we use a variable as the upper bound for our definite integral, then the resulting area can be thought of as a function of x, but that function of x is actually the antiderivative. So in particular, this means that we can calculate, again, when the top is some variable, we can calculate our area by using an antiderivative rather than one of those like crazy infinite Riemann sums, right? So we don't have to worry about sigma notation and taking limits to infinity and all of that stuff when we can instead use the antiderivatives, which are in some sense much more straightforward, at least sort of when we can calculate them, right? Because there are some examples where we might not be able to. Okay, so first part down, second part to go. That is that.